Signori, buongiorno. Oggi cominciamo a fare una trattazione dei processi che descrivono gli scambi tra le differenti matrici nei sistemi ambientali. La lezione di oggi si intitola l'equilibrio, devo farlo in inglese. Today, the lecture of today is named the equilibrium between spheres, and today we start discussing processes of exchanges of materials between the different environmental matrices. In particular, we may identify four ecospheres: the sky, land, surface water systems, and aquifers. So today we will introduce some of the processes of exchanges of materials between these spheres, and we will introduce the models, the general models we may employ for describing these exchanges. I said, we may subdivide the surface of our planet into four fundamental spheres: sky, land, water, surface water, and aquifer. More in particular, we shall start discussing the water cycle because, as you know, as environmental engineers, water is the most powerful solvent in our universe. So water is able to transport most of the chemical elements in different forms. This is why it is important to, in order to start to understand which are the key processes of exchanges between the different spheres, to describe the exchanges, to describe the water cycle. Trivially, we may say that water that is contained into the atmosphere, clouds, is given back to the surface of the earth through rain and snow, essentially. So from the atmosphere, we have a direct exchange that is called precipitation, that transfers water from the sky to the surface of the planet. This water may be found in forms of rain, so liquid water, or snow, it is iced water. From the planet surface, then we have several ways of water transport. The first one we may identify is overland flow. So this is water that is flowing through the surface of a planet. We have runoff. Runoff is water that is flowing through the surface of the planet, but not in the organized system. Overland flows refers to rivers, essentially, while runoff refers to water that is transported or transferred from the surface of the planet to the receiving water bodies. A third important pathway is that of groundwater. Groundwater is affected by surface exchanges through infiltration. Infiltration is a movement of water from the surface toward the subsurface. Infiltration moves water onto the subsurface, onto a water table. Then we have movement from the water table down to deep groundwater, and when groundwater flows, re-emerge on the surface water bodies, in particular lakes and oceans, through groundwater pathways. So we may identify these as groundwater flows. Once water has reached surface water bodies, then water is transferred back to the atmosphere through two principal processes that are evaporation and transpiration. Evaporation is direct phase changes of water from the liquid phase to the gaseous phase, while transpiration is the same transfer, but this transfer is mediated through plants that are organisms that may enhance or somehow control the water transfer between the surface of the planet and the atmosphere. So, from this introduction, we may identify the four spheres of the geochemical physical model of the Earth. You already know at least three of these spheres: the atmosphere, the hydrosphere, the lithosphere. And today, or in this class, we will introduce a fourth sphere, that is the biosphere. We may say that the area near the surface of the planet can be subdivided into four interconnected geospheres: atmosphere, hydrosphere, lithosphere, and biospheres. All these different geospheres may exchange materials. The main flow of exchanges of these materials is driven by water exchanges. So this is why it is very important to understand the characteristics of this very important solvent, that is water. Let's see what are these spheres. The atmosphere is the body of air which surrounds our planet. Most of our atmosphere is located close to the Earth's surface, where it is most dense. Okay, these are all trivial concepts, but it is worthwhile to recall them here. The air of our planet is 78% nitrogen and just under 21% oxygen. The small amount remaining is composed of carbon dioxide and other gases. It is remarkable to notice that this very important figure, 21% of oxygen in the atmosphere, as we already stated, as we already said, is a figure that is necessary, a percentage of water content, oxygen content of our atmosphere that allows oxygen respiration as a biological process as we know it today. So if the content of oxygen would be lower than 21% in the atmosphere, oxygen respiration as we know it today wouldn't be possible. And we know that oxygen respiration is one of the most impressive biotechnologies that have been introduced by bacteria in the process of changing the environment in order to adapt it to more complex and sophisticated living forms. It is also relevant to notice the fact that if the percentage of oxygen would be much higher than 21%, our planet, 21% in the atmosphere, our planet would be really a bad place to live in, because then we would have plenty of processes of self-combustion. I recall you that oxygen is a comburant, so in order to have combustion processes, there should be oxygen, and if a percentage of oxygen, the higher percentage of oxygen, the higher the probability of starting of processes of self-combustion. So if our atmosphere would contain a much higher content of oxygen than 21%, then we would live in a world of flames, ubiquitary and continuous combustion events. The hydrosphere, second sphere, is composed of all of the water on or near the Earth. This includes the oceans, rivers, lakes, groundwater, but even the moisture in the air. Here we have, if you want, an important concept that tells us that these four geospheres are not neatly subdivided by boundaries. Instead, these spheres are more likely more appropriately spheres that identifies the presence of some particular forms of chemical molecules. In particular, we include into the atmosphere, so into the hydrosphere, also this water that is diluted or dissolved into the atmosphere in the form of moisture, so clouds or humidity or wet contents in the atmosphere. 97% of the Earth's water is in the oceans, so it is salt water. 3% is fresh water. 3/4 of the fresh water is solid, so is in icy coverings and exists in ice sheets. So now you understand why it is so relevant, the issues of ice melting or glaciers melting, because glaciers are the reservoirs or the storages of fresh water. And you know that fresh water is a key or a very important chemical substance that is necessary for living processes to exist. 3% is fresh water, and of these, 3/4 is ice. The third sphere is the lithosphere. The lithosphere is the solid rocky crust covering the entire planet. The lithosphere is made up of inorganic and composed of minerals. It covers the entire surface of the Earth from the top of Mount Everest, this is more than 8,000 meters height, down to the bottom of the Mariana Trench, that is more than 13,000 meters deep in the Pacific Ocean. Then the final and more intriguing sphere is the so-called biosphere. Biosphere is that portion of the surface of the planet that contains all living organisms, plants, animals, and one-celled organisms like bacteria. All these are all part of the biosphere. Most of the planet's life is found from 3 meters below the ground to 30 meters above the ground, and in the top 200 meters of oceans and seas. The biosphere is the really new part of the story for environmental engineers. You are already familiar with the lithosphere, hydrosphere, and atmosphere, while the main subject of this class is the interaction with the biosphere. As I already said when I was talking of the hydrosphere, is also the case for the biosphere. We do not have neat boundaries separating these spheres. Instead, all these spheres are, to a certain extent, compenetrating each other. This means that, for example, in some portion of the surface that we may call it hydrosphere, you may find some portion of the biosphere, for example, living organisms that are living into the atmosphere, into the hydrosphere. This living organism pertains, from our point of view, to the biosphere. As I anticipated, one of the most relevant chemical substances that sustain, or if you want, are necessary for life to persist, is hydrogen oxide or water. We shall, since the beginning, make some consideration concerning the characteristics of this very particular chemical substance. A hydrogen oxide is made up of a large oxygen atom and two smaller hydrogen atoms. The shape of the molecule is this one depicted in this draw. The hydrogen oxide molecule is a highly dipolar molecule. Highly polar molecule. What does this mean? This means that this molecule has a very sharp, uneven subdivision of the chemical charge or of electric charge. In particular, the positive charges are around the hydrogen atoms, while the negative charges are in the proximity of the oxygen atoms. It is important to notice that most of the chemical properties of this chemical substance are due to this very particular dipolar or polar configurations, and in particular, this molecule, as you can say, has inspired several of our cultural heritage. For example, you may recall Mickey Mouse. Mickey Mouse has exactly the shape of a water molecule. What are the anomalies of this chemical substance? Water has a high melting and boiling temperature. It has a very high specific heat. This means that in terms of heat storage, has a very large capacity of storing heat, and you know that heat, as we have discussed last week, is a significant form of energy, significant for living systems, significant for several reasons, in particular for the reasons linked to the first principle of thermodynamics, so the energy conservation. So water has a very high specific heat. It is the substance that exists in more stable and metastable states, from crystallines to amorphous. It is an excellent solvent. Almost everything can be solved to a certain extent in water. This is why, as you know, we wash our hands, we clean our hands by washing them with water, because water can dissolve and transport most of the chemical substances. Hydrogen oxides, the very specific characteristics of hydrogen oxides are linked to the very special shape of this molecule. We said we have a large oxygen atom that is bonded with hydrogen bonds to the two hydrogen atoms. The angle between the two hydrogen bonds is of 104 degrees, and the dimensions of the distances between the center of the oxygen atom and the center of the hydrogen atom is less than 1 angstrom, so less than 10 to the minus 10 meters. So it is by studying these, if you want, morphological or spatial distributional characteristics of water, that we may justify several of the anomalies of water. For example, in this plot, we have we are linking the various characteristics of waters. We are describing how various characteristics of waters vary with temperature. For example, we shall start with the density of water, this blue curve. You all know that the maximum level of density of water is attained when the temperature is 4 Celsius degree. So at 4 Celsius degree, you have maximum density of water. This has as a consequence the fact that water that is a temperature different than 4 Celsius degrees has a density that is lower than the water at 4 Celsius degrees. And so as a consequence, we may find water floating, we may find hotter or warmer and cooler water floating on 4 Celsius degrees water layers. And this, for example, justifies and allows the presence of living systems even under ices, because you know that one of the most striking and impressive characteristics of water is that solid water, ice, is less dense than liquid water. So solid water floats on liquid water, and this has several consequences that are of relevance for living systems. For example, one of these consequences is that the water under ices are always at temperatures around 4 Celsius degrees, so that even under ice layers, we may find living organisms. Let's look, for example, at other characteristics like the specific heat of water. Specific heat of water has a minimum around between 30 and 40 Celsius degrees, and on all other temperatures, the specific heat is higher. And we justify what we have said, but water is one of the substances with the highest specific heat. So with the highest ability of absorbing heat. We may look, for example, at the viscosity. Viscosity of water reaches a maximum value around 20 to 30 degrees. Going below, the viscosity of water is increasing significantly. Okay, where do we find water in the biosphere? Water is of major importance in all living things. In some organisms, for example, so we are talking about the biosphere, up to 90% of their body weight is water. For example, in particular cases, let's look at humans. Up to 60% of the human body is water. The brain, a human brain, is composed of 70% of water, and the lungs are nearly 90% of water. About 83% of our blood is water, which helps digest and transport by dissolution the food. and transport also the waste is produced by cellular processes or cellular bioprocesses. This is another reason that when of the fact that water has a high specific heat is also explaining why water is an important controlling element for body temperature. Body temperature is regulated by the large amount of water because water having a large heat capacity can store water and so can absorb temperature variations very effectively. Each day, humans must replace 2.4 liters of water, some through drinking and the rest taken by the body from the foods eaten. So please drink at least one, better if 2 liters of water per day in order to keep your health in good shape. Let's now look at other substances, for example, that are of relevance for environmental engineers. Let's now give a look to some toxic substances. In particular, one important class of toxic substances is that of heavy metals. Heavy metals are chemical elements that have the following characteristics: densities exceeding 5 grams per cubic centimeters. They generally behave as cations, so they have a positive charge. They have a remarkable ability to form complexes. So this means that they have a remarkable ability to be immobilized into complex chemical complexes. They have low solubility of their hydrates. So heavy metals hydrates are quite stable compounds. Different oxidation states depends on pH and EH conditions. They have a great affinity for sulfides in which they tend to concentrate. So if your problem as an environmental engineer is a problem of heavy metal contamination, then the regulating forcing functions are pH and the concentration of sulfides. These elements belong mainly to transitional elements in the group 6 to 7b, 7, 8, 1 and 2b, but also some groups 3 and 5, 3 and 4a. In general, if this is the table of the elements of Mendeleev, the heavy metals are those identified by this square. Of course, this is again is not a shape or a neat subdivision because there are other elements that may behave partially as metals, like for example aluminum, but they are not into this subdivision. But anyhow, aluminum is considered also to be a heavy metal or a toxic substance. The basic parameters that regulate the ability of soils to store heavy metals, as we have already said, is pH, is the redox potential, is the content of organic matter, and is the cation exchange capacities. In particular, the content of organic matter, as we will see when we will discuss ecotoxicities, or when you study ecotoxicological processes, is one of the relevant aspects regulating the exchange of heavy metals between the lithosphere and the hydrosphere. Okay, for the environmental engineer, it is of relevance. This kind of figures are of relevance in order to assess if there is a toxication event or a contamination situation. For example, for the restoration of polluted sites, these are the different concentrations to be expected in milligrams per kilograms of soil for the different elements, with cadmium, chromium, copper, nickel, lead, and zinc. These are the average contents, and these are the limitation indicated by public by laws in order to consider contaminated or not contaminated the sites, the soils, in as a function of the use. For example, these figures refers to the limitations of heavy metal contents for soils in the public or private or residential green areas. While, as you see, these are higher concentration, these are the limit values in concentration for soils that pertains to commercial and industrial sites. So if you want to evaluate soil contamination by heavy metals, you may find in the laws, in environmental laws, in particular this refers to laws number 471, 1999. Now this law is including again in 152, 2006. So you can find tables of limit values. A very important point of the preceding decree is that concerning the choice of remediation techniques. In particular, Article 4 of that decree established the obligation of reclamation and environmental restoration. It is stated that the interventions for remediation and environmental restoration of a polluted site should give priority to the use of techniques that promote the reduction of the handling in situ treatment and the reuse of the soil, subsoil, and landfill materials subject to remediation. So the idea is that of trying to reducing the concentration of these metals in situ without transporting or moving these materials, because as you may know as an environmental engineer, if you have a contaminated soil and then you remove or you take away these soils, then you end up with special wastes, and special wastes are very difficult to handle, especially in terms of cost, are very costly to handle. So let's go back to argument the equilibrium between spheres, and now let's focus about the exchanges of toxic substances that are present in the various forms in the different spheres. I recall you that the different spheres are lithosphere, hydrosphere, atmosphere, and biosphere. Toxic substances that are of relevance for environmental engineer practice are heavy metals or persistent organic pollutants, or polycyclic aromatic hydrocarbons, pesticides, but in general also nutrients or the effects of drugs and so on, or emerging contaminants like is the case of perfluoroalkylic PFAS. Various spheres can be in equilibrium between them, or there may be dynamic exchange phenomena. The practice of environmental engineer for defining and studying these exchange phenomenon starts from the observation that the exchanges between the spheres are usually described by relations between equilibrium concentrations the transfer of a compounds from one sphere to another one takes place until the equilibrium concentrations are reached. So the equilibrium concentrations may be seen as endpoints of the transfer processes. The rate of a transfer process is generally proportional to the distance of the concentration from the equilibrium concentration itself, and depends on the diffusion coefficients of the compounds and on the resistance at the interface between the spheres. So here there are two important concepts. The characteristics that you have to include into your model to describe the exchanges between the spheres are for sure the distance from equilibrium concentrations, so that you can estimate the rate of exchanges, but also the characteristics of the interface. The characteristics of the interface are described by the diffusion coefficients and by the resistance at the interface between the spheres. The resistance at the interface and the diffusion coefficients depend dramatically on the temperature, on the area exposed to the atmospheres or to the liquid volume, and on the rate of the flow. So the rate of the flow, the extension of the interface, and the characteristics of the interface in terms of resistance are both but regulates the characteristics but regulates the exchanges between the spheres, and all these characteristics depends dramatically on the temperature. So in this case of in the description, the modeling description of these processes, temperature shall always be included as a driver. Now let's, as a forcing. Now let's go into the detail of some processes or some models describing this type of exchanging. First of all, we shall focus on the hydrosphere-atmosphere exchanges. The hydrosphere-atmosphere exchanges, as you already know, is described by Henry's law. So the environmental engineer that is building a model describing exchanges between hydrosphere and atmosphere will first of all resort to the Henry's law model. Henry's law model tells us that the concentration in the liquid fraction is equal to the partial pressure divided by the Henry constant. Or you may rewrite it by writing that, implying the first law, the law of perfect gases, P times V equals nRT. You may write that the concentration in the atmosphere divided by the concentration in the hydrosphere is equal to the Henry constant divided by RT, so by the temperature at which the exchanges takes place. The Henry constant is a characteristics of the substance itself. So you may classify all these toxic substances, heavy metals, persistent organic pollution, pollutants, polycyclic aromatic, and so on, in terms of their value of Henry constants. How do we build this model? This model is derived by the Whitman's two-film theory. So we may describe the flow of the substance at the interface within the two phases. So we may describe it, our model we may describe the interface transport as the flows per unit area. So we may explicitate that the flow in the liquid phase is equal to a constant of equilibrium KL times the difference in concentration between concentration at the interface and the concentration in the liquid phase, while the flow in the gaseous phase in and out the gaseous phase is equal to equilibrium constant Kg divided by RT multiplied by the differences in the partial pressures in the gaseous and in the at the interface of the substance. Then we employ Henry's law, and we use a constraint that is the constraint of a steady state exchange. So in a condition in steady state in which the flow through gaseous phase and through the liquid phase are equal, so we may call these two flows Jg and Jl equal to capital J. So we may reverse this equation, calculate the flow as a difference between the partial pressure divided by Henry constant, that is the characteristics of the substance, minus the concentration of the substance in the liquid phase, divided by this quantity that may be seen as a resistance, a series resistors. So we have a resistance in the liquid phase that is described by RT divided Kg divided by the Henry constants, plus a resistance in the gaseous phase that is described by the inverse of equilibrium constant Kl, that describes exchanges between the interface and the liquid phase. So what we are doing here, we are trying to describe what happens at the interface. So we have, here is the gaseous phase, is the liquid phase. We describe the interface by expanding these infinitesimal boundaries into a liquid interface and to a gaseous film interface, the liquid film and the gaseous film of an infinitesimal thickness. This is the interface. You describe the force that pushes the movement from the gas bulk to the gas film by employing partial pressures. You describe the forces that pushes the movement from the liquid bulk to the liquid film by employing concentrations. And by writing this, you may explicitate the flow by defining the flow in the liquid film and the flow in the gaseous film as function of equilibrium constant Kl and Kg multiplied by driving force that is proportional to the difference in concentration in the case of a liquid film and to the difference in partial pressure in the case of a gaseous film. Then you assume a steady state. So you assume that there is an equal flow from gaseous phase to the liquid phase and vice versa. And then you reverse this equation and you obtain a very interesting description of the interface transport by writing that the flow is equal to the difference of a potential difference that may be represented by a force, partial pressure minus liquid concentration, divided by a series resistors. If you want, this is an analogous of the Ohm laws for current transfer applied to interface transport at the interface. Transport at the interface. With the Whitman two-field theory, we may classify different pollutants, substances, as we have said, in function of the Henry constant value. So if, for example, we may plot the percentage resistance in the liquid phase, so the ratio between the resistance in the liquid phase divided by the total resistance, RR plus RG, as a function of Henry constant. As I told you, Henry constant is a specific characteristic of the various substances. So, all the substances, like for example, dieldrin and linden, these are chemicals, they're pharmaceuticals, or nitrite or aldrin or DDTs and so on. All these substances have different values of the Henry constant. You have a kind of asymptotic behavior, a sigmoidal curve, describing the percentage resistance as a function of the Henry constant. Here, the Henry constant is expressed in atmosphere per cubic meters per mole. So you may classify different substances as soluble substances, that are those substances that display a Henry constant that is less than 10 to the minus 5, and insoluble constancies, the substances that are these substances that display a Henry constant above 10 to the minus 3 atmosphere per cubic meters per mole. Then you may say that insoluble substances, the flow of insoluble substances is generally liquid controlled, meaning that it is the concentration in the liquid that is the main driver of exchanges, of exchange phenomena between the hydrosphere and the lithosphere, while for substances that display that are soluble, then you have a gas-controlled process, so it is the partial pressure of the substance, but it is the main regulating force that governs the flow between the hydrosphere and the atmosphere. So this is the very general model describing the interface transport between the hydrosphere and the atmosphere, and this is obtained through the Whitman's two-theme theory and simply applying the Henry laws. Of course, by increasing the Henry constant, we do not have a linear behavior. Instead, we have a kind of sigmoidal shape, but the sigmoidal curves may be displaced. There is a form of hysteresis depending on the characteristics of the water body. In particular, from practical experiments, we know that for Great Lakes, so Great Lakes are water bodies for which there is only a significant radiation or volatilization phenomena in the topmost layer, then the curve is this one. While for small sheltered lakes, small lakes that are protected from wind effects, so sheltered, the curve linking the percentage resistance in the liquid phase is this one. So there is a displacement of this sigmoidal curve depend on the water body characteristic. So you understand the complexity of this type of processes forces you also to include the characteristics of the water body that you are studying, which you are studying the exchange processes between hydrosphere and atmosphere. In particular, for the volatilization process, that is the process of exchange of the one directional processes of exchange of material from the liquid phase to the gaseous phase, we may rewrite the equation that we have derived here in this form. in which we write that the variation of the concentration in the liquid phase is equal to the velocity of volatilization times the surface of the interface times the difference in partial pressure and the difference in the liquid concentration of a particular substance. Of course, if you want to make this operation, we have to fix the dimensions of a partial pressure, so this pressure, in order to make it consistent with the concentration. So this is why we have to divide by employing the Henry law. In this case, we rewrite the law coming from the two interface, sorry, the two film theory at the interface in this way. So we may assume, and we know that for toxic substances of concern for engineers, in general, the partial pressures are almost zero, so can be approximated to zero. So what it is most relevant, it is the concentration in liquid. So these are liquid controlled processes. For these liquid control processes, we rewrite the model and we may obtain the speed of volatilization by reversing this equation. And we see that the speed of volatilization depends on the constant of exchange in the liquid phase times the Henry constant, that is a characteristic of the substance, divided the Henry constant plus RT multiplied by the ratio between the equilibrium constant in the liquid phase divided by the equilibrium constant in the gaseous phase. By experimental observation, we know that these constants may be made, may be expressed as transfer coefficient as functions of the densities of the particular substances in the liquid and the gaseous phase, and on the resistance of these particular substances at the interface. In general, we know that by experimental observation that KL is proportional to the molecular weight of the substance elevated to 1/4, while Kg is proportional to the molecular weight of the substance elevated to 1/4, but time, this is the wind speed. So in the gaseous phase, also the wind speed has a relevant importance in terms of exchange, because of course the wind, stronger wind, enhance the process of volatilization. So what we are writing here is the equilibrium constant in the liquid phase is equal to the equilibrium constant of exchange between the liquid sphere and oxygen, multiplied the molar weight, while in the gaseous phase we have the same dependence on the molar weight multiplied by the wind speed that is acting on the surface of the water body. By doing this analysis, we may again classify different substances in terms of their volatilization rate. For example, we may plot the volatilization rate of different substances as a log function of the Henry constant. So we see that if we fix, for example, the wind speed on the water body at 5 meters per second, then we will have these different types of shapes linking the volatilization rate to the Henry constant for different molar weights. So heavier the substance, or increasing more molar weight for the substances, then we have increasing values of the volatilization constant at the fixed values of wind velocity. Again, this is a distinction between soluble and insoluble substances. Here we are classifying a lot of different chemical substances. I think you know these box and whiskers diagrams. These box and whisker diagrams are resuming in a simple picture a lot of statistics concerning several different statistical characteristics of the substances. So, for example, for halogenated aliphatics, we know that the median value of a log Henry constant is this one, while we know that the interval from the minimum to maximum Henry constant for the class of halogenated aliphatics are represented by these whiskers, these mustaches. Okay, I hope you can read these pictures. From these observation from these types of graphs, we may classify or we may find indication of where to put in terms of solubility or insolubility, in terms of gas controlled or liquid controlled flows, the various substances by knowing their Henry constants. And I recall you that the Henry constants are characteristics typical of the various substances as summarized in this picture. So this more or less ends up the model describing the exchanges between the hydrosphere and the atmosphere. Now, or better, next lecture, that will be on Thursday, we will describe the exchanges between the lithosphere and the hydrosphere. You already know this process. This process is called adsorption, and we have we have one general model of adsorption and three particular specific models that are isothermal model. So these models are models for which the temperature is considered constant. The Freundlich, the Langmuir, and there is another isotherm that I do not recall now the name. Redlich-Peterson, Freundlich, Langmuir, and Redlich-Peterson isotherms. And then we have a very general model that is the partition coefficient model that we may start introducing it in the case of adsorption process that is describing the exchanging between the lithosphere and the hydrosphere. Okay, do you have any questions? If you do not have any questions, I would stop my lecture here today. I stay 5-10 minutes in the class, so you have time for formulating your questions. Otherwise, I close the classroom and we will see next Thursday.